Hi everyone. In this video, we'll be discussing convergence tests for series with positive terms. In particular, we'll learn to utilize the tests for divergence to determine if a given series diverges. We'll learn to utilize the integral test to determine if a given series converges or diverges. And we'll also be able to analyze the strengths and weaknesses of each of these tests. So before we get started, I want to return to a point that we made in a previous video, which is that it can be hard to tell to begin with whether or not a series converges or diverges, let alone what value it converges to if it does indeed converge. So what we're going to start dealing with is that first question of trying to determine whether or not a given series converges or diverges. If you know that a series converges, then you can feel somewhat confident that you can approximate the value that it converges to by simply taking a very large partial sum. So even though it maybe seems not so helpful to just know that a series converges but not know what it converges to, in fact, it can be quite helpful because it gives us a sense of assurance that our computational results likely approximate the true value of the infinite series. So again, in this particular video and in subsequent videos, we're really going to be focusing on determining whether or not a given series converges or diverges, and we're not going to worry so much about what it converges to if it does converge. All right. So combining these, what we'd really like is a test that would tell us, okay, if I look at a series, here's how I can know whether or not it converges or diverges. And so over the next several videos, we're going to look at a number of different tests. These tests have sort of different strengths and weaknesses, but we'll look at a number of different tests to help us to determine whether a given series converges or diverges. Now, when we talk about tests for convergence, the name's a little bit misleading. Not all of our tests are going to allow us to conclude that a series converges. Not all of our tests will allow us to conclude that a series diverges. And a number of our tests will only apply to certain kinds of series. So when I say a test for convergence, what I really mean is a type of test that may apply to some particular types of series and may help us to determine something about convergence. It could help us determine that a series does not converge. It could help us determine that a series does in fact converge. It may only apply to very limited types of series. But again, we're going to sort of roughly lump all these together and call them tests for convergence. It's going to be really important for each test to pay attention to the hypotheses and the conclusions of that test. So what I really mean here is we're going to need to be really careful to note when we can apply the test and exactly what the test allows us to conclude, right? So sometimes the test may allow us only to conclude that a series diverges. Sometimes it might allow us to determine that in some cases it converges and in some cases it diverges. Again, we're going to be learning a number of tests. We're going to start with a couple in this video and more in subsequent videos. As we get further along, I will post a handout with all of the different tests so that you can have one handy reference for all of those. All right, so we're going to begin with something, it sort of has, the book refers to it as the test for divergence. It's also commonly referred to as the nth term test. So this test says if the limit as n goes to infinity of a sub n is not equal to 0, then the series sum of the an's diverges. Okay. So before we get into this example, let's sort of think about what's going on here. So this says if the terms of your series, so an, these are the terms of your series. If the terms of your series are approaching some value that's not 0, then your series must diverge. Okay, so let's start with this example right here. So we have the sum n squared plus 1 over 2n squared minus 1. Now, the first thing you may pause about is I don't have any limits here. Okay, now we're going to assume throughout this video and subsequent ones that we're talking about an infinite series. And it actually, in terms of convergence and divergence, does not matter what value we start at. So whether I start at 1 and go to infinity, or whether I start at 17 and go to infinity, or whether I start at 53 and go to infinity, does not affect whether or not this series converges or diverges. What it does affect is what it converges to, if it converges. But again, we're not sort of focused on that right now. So we're going to drop the limits on the sum, and we'll just assume that it is an infinite sum. And so really these tests are going to help us conclude whether or not these series converge or diverge. Okay. So in this case, this test says if the limit of the terms is not 0, then the series diverges. So here, what I would do is I would look at the limit as n goes to infinity of n squared plus 1 over 2n squared minus 1. Okay. Now, this is a case where this is a rational expression. I can divide every term in the top and bottom by the highest power of n, or n squared. So I get that this is equal to the limit as n goes to infinity of n squared divided by n squared is 1, plus 1 over n squared, over 2n squared divided by n squared is just 2, minus 1 over n squared. And so now I see as n goes to infinity, this term will go to 0, and this term will go to 0, and I'll be left with 1/2. So what I see in this case is that this limit is 1/2, which is not equal to 0. And so I could say here that the series diverges by the divergence test. Now, divergence test. Since the limit of the terms is equal to 1/2, which is not 0. Okay. So again, what this test says is if you take the limit of your terms and you get something that's not 0, then the series must diverge. Now, why is this true? One way to think about this is as you go further and further out, this says your terms are approaching 1/2. So as you get really far out in your series, it's almost like you're adding 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And if you add 1/2 an infinite number of times, that sum is going to go off to infinity. Okay, so essentially, if your terms are going off to some value that's not 0, then it's like you're adding a whole bunch of non-zero things together. And in fact, non-zero things that are like bounded below by something that's not 0. And so the sum of those must be going to infinity. All right. Now let's look at another example and see what we can say via the test for divergence. So let's look at now this sum. The sum n squared plus 2n plus 3 divided by n cubed plus 3n plus 1. Okay. Now again here, I want to know in this case just what does the test for divergence tell me, or the nth term test tell me about this series. So I'm going to look at the limit as n goes to infinity of n squared plus 2n plus 3 divided by n cubed plus 3n plus 1. Now, I'm going to play sort of a similar trick I've played many times now. I'm going to find the highest power of n, that's n cubed. I'm going to divide every term by n cubed. Be equal to the limit as n goes to infinity of n squared divided by n cubed is 1 over n. 2n divided by n cubed is 2 over n squared. 3 divided by n cubed, all divided by, now I have n cubed divided by n cubed is 1, plus 3n divided by n cubed is 3 over n squared, plus 1 divided by n cubed. Okay. Now, all of these terms are going to go to 0. Okay. And so what I'm left with in the limit is 0 over 1, which is 0. So in this case, I see that the limit of my terms is 0. So what does the theorem tell me? Well, remember, the theorem said if the limit as n goes to infinity of an is not 0, then this series diverges. Okay. But it didn't say anything about what happened if the limit was 0. Okay. And in fact, you cannot conclude anything via the test for divergence about this series. Okay. It is not the case, it's tempting to think, but it's not the case that if the limit is 0, it converges. That is false. Okay. The harmonic series, sum of 1 over n, the limit of those terms is 0, but that series diverges. The sum 1 over n squared, those terms go to 0 and it converges. So when the limit of the terms is 0, you don't know whether it converges or diverges. And the test for divergence, one reason I sort of like that name is it tells you the only thing you can ever conclude from that test is that a series diverges. You can never conclude from that test that a series converges. So here, I would say that the test for divergence is inconclusive. Basically, it doesn't really tell me anything inconclusive. It doesn't tell me anything about whether this series converges or diverges. Now, we're going to develop tools before too long that will help us deal with a series exactly like this. But for now, the test for divergence doesn't tell me anything about the convergence or divergence of that series. I just don't know. All right. Now that you've seen a couple of examples, let's pause for a knowledge check. What does the test for divergence tell you about the series 1 over 4 plus n squared? So I'm going to pause here. I want you to use the test for divergence to determine what it tells you about this series. Okay, great. Let's take a look. So if I look at the limit of the terms, the limit as n goes to infinity of 1 over 4 plus n squared, I can again divide by the highest power of, well, I could divide by the highest power of n if I wanted to. But actually, if I look at this, I'll see the top is fixed at 1. The bottom, as n goes to infinity, is getting larger and larger and larger. This limit is going to 0. And so again, when the limit of the terms goes to 0, the test for divergence tells you nothing. So here the test for divergence is inconclusive. Okay. So again, we'll need to try some other things to eventually determine whether or not series that look like this converge or diverge. Now, the nice thing about the test for divergence is it's fairly straightforward, right? If the limit is not 0, then the series diverges. The only possible conclusion is that the series diverges. You can't conclude anything when the limit as n goes to infinity of the terms is equal to 0. The series could still converge or it could diverge. It's very nice for its simplicity, right? Again, the limit is not 0, then the series diverges. However, it's also limited in the number of circumstances where it does apply, and it never allows you to conclude that anything converges. So it's sort of a quick and dirty test that might sometimes help you out and allow you to say, oh, this series definitely diverges because the limit of the terms is not 0. However, oftentimes you calculate this limit, you find that the limit of the terms is 0, and then the test for divergence doesn't help you at all, and we need other tests to help us out. Okay. So let's look at one of those other tests. So the next test we're going to discuss is what's called the integral test. So suppose that your terms in your series an are equal to some function of n for all positive integers n, where this function f is continuous, non-increasing, and positive on the interval from 1 to infinity. Then if I look at the improper integral from 1 to infinity of f of x dx, and I look at the infinite series of ANs, then either that integral and the series both converge or the integral and the series both diverge. Said another way, the improper integral and the series behave the same. They either both converge or they both diverge. Now, to sort of see why that's true, sort of imagine you're in this situation and you have some series, sum of ANs. Okay. Now, you create this function f of x, right? And this function f of x, right, it should be continuous, non-increasing. So it doesn't have to necessarily be going straight down, but it can't be going up. It could be flat. But in this case, I've just drawn it as decreasing. It's continuous, decreasing, and it's positive on 1 to infinity. Now, what I know is that, say, when I plug in 1 here, my height is A1, the first term in my series. When I plug in 2, my height is A2, so on and so on. Okay. And so what I actually get here is, if I think about sort of a Riemann sum approximation here, if I drew the Riemann sum where the bases are all 1, and they sort of go 1, 2, 3, 4, so on and so on, I would get here that this Riemann sum is actually just this series. So this series is like a Riemann sum approximating this integral. Now, to formally prove the integral test, you need to be a little more careful, but the rough idea is that there's some relationship between this series and this integral, which allows us to conclude that if this improper integral converges, the series has to converge, and if this improper integral diverges, then this series has to diverge. So let's see in practice how we can take advantage of the integral test. So to start with, let's revisit a series we've looked at before, the sum of 1 over n squared. Now, we mentioned in a previous video that this does converge. It converges to pi squared over 6. What we really want to focus on here is how we can use the integral test to help us determine that it converges. Okay? So again, the first thing you need is this sort of related function. And the way you're often going to get it is just swap out the n for an x. So if I look at f of x is equal to 1 over x squared, okay, I will note that that meets all of my conditions. So what are my conditions? F of n should be equal to a of n. Well, if I create my function by just swapping the n for an x, that's always going to be true. So that part is true. My f should be positive. It is 1 divided by something that's always positive, right? So that'll always be positive. It should be continuous. It is continuous on 1 to infinity. The only place where it's discontinuous is at 0, but I only need it continuous on the interval from 1 to infinity. And I need it to be non-increasing. In fact, this is decreasing. As x increases, the value of this decreases. So this is a decreasing function that meets all of our conditions. So what the integral test says is we'll look at then the integral from 1 to infinity of f of x dx. So in this case, this is the integral from 1 to infinity of 1 over x squared dx. Okay. Well, now this is just an improper integral. I know how to deal with this. This is the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. Okay. The antiderivative of 1 over x squared is negative. Sorry, I need to keep the limit along with me. So limit b goes to infinity of the antiderivative would be negative 1 over x, evaluated at b and at 1 and take a difference. So this is the limit as b goes to infinity of minus 1 over b plus 1. As b goes to infinity, this term goes to 0, and so this limit is 1. Now, what's important here is not the 1. What's important here is that this integral converges, okay? And so since this integral converges, since this integral from 1 to infinity of f of x dx converges, this series and so maybe actually let me write this here with the actual function. So since the improper integral 1 to infinity of 1 over x squared dx converges, then the sum 1 over n squared also converges by the integral test. So in this case, this is really nice because I get to sort of swap out this question of does this series converge or diverge for this question of does this improper integral converge or diverge. Now, I mentioned this value of 1 is not important. What's important is that it's some finite number. And the reason this is really not important is this series doesn't converge to 1. Okay, I already told you in an earlier video, this converges to pi squared over 6. So this value is sort of not important for the fact that it's 1. It's important because I get some finite value and this improper integral converges. Therefore, the series must also converge because the integral test tells me that the series and the improper integral of the related function either both converge or they both diverge. And now I know that this improper integral converges to 1. And so therefore, this series must also converge by the integral test. All right, let's look at another example. And this is actually the same series from the knowledge check earlier. We applied the test for divergence to this series, and the test for divergence was inconclusive. So now we want to look at, what might the integral test tell us about this series. The first thing I need is a related function. Again, best and easiest way to get this is just to swap out the n for an x. Okay. Now I can check, this is continuous, this is positive, this is decreasing on 1 to infinity. So this meets all the conditions, and importantly, f of n gives me the terms of my sequence or my series here. Okay. So now what I need to do is I need to look at this integral from 1 to infinity of f of x dx. So that's the integral from 1 to infinity of 1 over 4 plus x squared dx. Okay. Now, this is going to be the limit as b goes to infinity, the integral from 1 to b of 1 over 4 plus x squared dx. All right. Now, before I can do any of that, the first thing I'm going to need is to find an antiderivative of this function 1 over 4 plus x squared. Now, you've done enough of these that you may even just sort of be able to guess this by now, but let's take it step by step. I see a 4 plus x squared in that denominator there. That sort of makes me think this might be a trig sub. Okay, and so in fact, I'm going to set x equal to 2 tangent of theta. If I do that, my dx will be 2 secant squared theta d theta. And after making that substitution, I'll end up with the integral of 1 over 4 plus 2 tangent theta squared times 2 secant squared theta d theta. I think my d theta ran off the edge there. Okay. I'm going to skip a little bit of the algebra, right? Or skip writing it out. When I plug this in here, I'll get a 4 tangent squared theta. This is going to give me a 1 over 4 secant squared theta. I'll have a times 2 secant squared theta d theta. And so all of this is going to simplify to the integral of 1/2 d theta. That's going to be 1/2 theta plus c. But now if I look back up here, I can solve for theta. Theta is tangent inverse of x over 2 plus c. All right, great. Now, coming back to my original problem, I have an antiderivative, right? So this ought to be the limit as b goes to infinity of 1/2 tangent inverse of x over 2 evaluated at b and 1 and take a difference. This ought to be the limit as b goes to infinity of 1/2 tangent inverse of b over 2 minus 1/2 tangent inverse of 1/2. Now, as b goes to infinity, this is going to go to infinity, and the input of tangent inverse goes to infinity, this goes to pi over 2. So this becomes, oh, sorry, I'm taking the limit now, so I can drop the limit. This will be 1/2 times pi over 2 minus 1/2 tangent inverse of 1/2. Now, here's the beautiful thing about this. I don't care what that value is. So I don't need to simplify that anymore because I now know that's going to a finite value. So this integral converges. And so by the integral test up here, we can determine that this series also converges by the integral test, since the integral from 1 to infinity of 1 over 4 plus x squared dx converges. So whereas the test for divergence was inconclusive here, the integral test here actually allows us to conclude that this series does in fact converge. So in summary, in some ways, this is a great test because I get to determine whether or not a series converges or diverges by looking at the associated integral. And we spent plenty of time talking about whether improper integrals converge or diverge. On the other hand, this is a terrible test because I'm trading out a series problem for an integration problem. And we also know that like integrals can be very difficult. And I may not be able to, for example, find a nice antiderivative that I can really work with. So again, advantages and disadvantages. I think when I think of the integral test, I often think, if I look at the terms of the series, and that would make a function I can find a nice antiderivative of that I can integrate, then the integral test might be really helpful, right? And it's really helpful because I can conclude either convergence or divergence, right? If I can determine whether that improper integral converges or diverges, that's going to tell me exactly what the series does. However, if it's not something I can easily integrate, then this is not going to be a helpful test at all. Okay, so it is sort of important to keep those things in mind. Now, from the integral test, we can actually derive sort of a quick and dirty test called the p-test. which helps us to determine if certain types of series diverge. So if you sort of think back to the series, we've looked at several series of this form, 1 over n to some power. The integral test tells us the convergence or divergence of those will be the same as the convergence or divergence of this. Well, from looking at these improper integrals, we know that this will converge. This converges if p is less than 1, and it diverges if p is greater than, sorry, I have that backwards. This converges if p is greater than or equal to 1, and it diverges if p, nope, sorry, let's get that right. So it converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. Well, the integral test tells us the same must be true over here then. Okay, and so the p-test, which we'll sort of refer to quite a bit moving forward, just says, well, if I have the series 1 over n to some power, that's going to converge if p is greater than 1 and diverge if p is less than or equal to 1. So, note that this only works for a very particular type of series, right? But when it does work, it's just a sort of quick rule to help us to determine convergence or divergence. And really, it's just an application of the integral test, but it's one we're going to reference so often that it's worth sort of having its own name. Now, we'll remark here, right, this is how we now know the harmonic series diverges. So the harmonic series, sum 1 over n, that's the case p is equal to 1. So when p is equal to 1, right, I get the harmonic series here. That's the same as looking at this integral, and because p is equal to 1 there, that series diverges, which tells you that the harmonic series also diverges. So you actually get divergence of the harmonic series from the integral test. It's also a case of the p-test, but again, the p-test really is just an application of the integral test. We're going to stop there. The homework and the quiz will have opportunities for you to practice applying both the test for divergence and the integral test. And as always, if you run into problems on the homework or the quiz that you're having difficulty with, or if you just have any more questions that weren't answered in this video, please feel free to reach out.